Good morning, all, and welcome you all for this evening. Any successful event is incomplete without a prayer. So I now call upon Dr. Khalid Wahid, Assistant Professor, School of Arabic and Islamic Studies, to recite the Qiraat.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم يا أيها الذين آمنوا لا يسخر قوم من قوم عسى أن يكونوا خيرا منهم ولا نساء من نساء عسى أن يكن خيرا منهن ولا تلمزوا أنفسكم ولا تنابزوا بالألقاب بئس الاسم الفسوق بعد الإيمان ومن لم يتب فأولئك هم الظالمون يا أيها الذين آمنوا اجتنبوا كثيرا من الظن إن بعد الظن إثم ولا تجسسوا ولا يغتب بعضكم بعضا أيحب أحدكم أن يأكل لحم أخيه ميتا فكرهتموه واتقوا الله إن الله تواب رحيم. O believer, no man should laugh or mock at other men. The latter may be better than the former, and no woman should laugh at other women. The latter may be better than the former. Do not defame or insult one another, and do not call one another by offensive nickname. What a bad thing to call dirty name after faith. Whoever does not repent, they are indeed wrongdoers. For believers, avoid much suspicion. Indeed, some suspicions are sin, and do not spy nor backbite one another. Would any of you like to eat flesh of his dead brother? No, you would hate it. Fear the God. The God is the acceptor of repentance, the most merciful. Thank you.
This event has been made possible with the help of the backbone of our department, our beloved HOD, Dr. E. Syed Mohammed, Professor and Head of CSC Department, BSA, Crescent Institute of Science and Technology, and the coordinator of the FDP. I now request our HOD to give the welcome address.
Not audible. Dr. Saeed is not audible.
HOD, sir.
Hi, sir. Good morning. Assalamu alaikum to all present here. It is my privilege to welcome you all on behalf of the Department of Computer Science Engineering, BSc Crescent Staff Science and Technology, Chennai, Tamil Nadu. BS Abdur Rahman Crescent Staff Science and Technology is a quality leadership institution. Through our long history of 36 years of excellence, the institute has offered access to a wide range of academic opportunities. With 46 programs grouped under 12 different schools, 27 undergraduate programs, 19 postgraduate programs, and PhD in all the departments. The Department of Computer Science and Engineering was started in 1990. The department offers four degree undergraduate programs, namely BTech CSC, BTech CSC IoT, BTech CSC Cybersecurity, BTech Artificial Intelligence and Data Science. The department also offers the postgraduate degree program and doctoral degree program in the field of computer science engineering. The undergraduate and postgraduate program of the Department Computer Science Engineering are approved by National Board of Accreditation, New Delhi. I heartily welcome to our chief guest, Dr. Sitabhra Sinha, Professor, Institute of Mathematical Science, Chennai, and he will deliver the keynote address of 1 week faculty development program on data science from 21st September to 25th September 2020, sponsored by Atal AICT. It gives me immense pleasure to extend a hearty welcome to our respected Pro Vice Chancellor, Dr. A. Pir Mohammed sir, and Registrar Dr. A. Acha sir, respected Senior Manager Mr. V.N.A. Jalan sir. I extend a warm welcome to Dean School of Computer Information and Mathematical Sciences Dr. Venkateshan Chellam sir, and all Deans, HOD, Faculty of Computer Science and Engineering and other departments. I am very happy to welcome faculty members from various institutions, research scholars, and industry people. We look forward to successful faculty developer program over the next 5 days, and I strongly encourage you all to become actively engaged in various sessions and discussion on the data science. We have arranged the research person such a manner to fulfill the current scenario of data science. We have invited research person for FTP from Tamil Nadu, other state, and foreign country, China and Singapore. To learn more practical knowledge in data science, we have arranged the data scientists from industries. The objective of faculty development program to solve complex challenges with the data and to drive important decision-making processes, to improve the professional skill in data analytic and learn machine learning in exploding, to merge and analyze large volume of business-centric data from heterogeneous source to ensure the consistency of the data set, build mathematical model, perform statistical analysis, apply machine learning algorithm, and create visualization to communicate the insight to key stakeholders. Industry perspective of the applying machine learning algorithm in data science field. In-depth analysis of medical image data using deep learning algorithm to select a good machine learning model, and finally, learning tools that allow the organization to streamline security. Thank you all, and I wish you a very successful faculty development program. I warm welcome you again. We wish the very best to all participants. Have a great day. Thank you.
Thank you, sir. I now request the Honorable Pro-Vice Chancellor, Dr. A. Said Mohammed, to deliver the inaugural address.
Good morning, all of you. Today's chief guest of the function, Professor Sitabhra Sinha, our registrar, Professor Azad, and Professor Venkateshan Selvam, the Dean, School of Computer Information and Mathematical Sciences, and Dr. Syed Mohammed, Professor and Head Department of Computer Science, and the members of Program Committee, Organizing Committee, and other Dean Directors, HODs, and faculty members of our institute, and the participants from different institutes. It gives me immense pleasure to participate the inauguration of a 1 week faculty development program on data science organized by the Department of Computer Science and Engineering. Of course, I congratulate the organizing committee and particularly the HOD, Dean, and the members of the program committee for organizing such a relevant program at the right time. So this year, all of you know that we have introduced 3 new programs as told by our HOD: Artificial Intelligence and Data Science, and Beta Computer Science Cyber Security, Beta Computer Science and Internet of Things. So more and more such programs are required to popularize the importance of the data science. Of course, no need to emphasize the importance of the data science in the present context, because science is all about prediction. So finding relationship between the cause and effect, of course, is done long back. This is a normal pursuit of every scientist actually to associate the effect with the cause. Normally, less number of influencing parameters would be available between the cause and effect. So, some based on theories and laws, it would be possible to relate. Now, the things are becoming more and more complex. The sheer volume of the data available and the diversity and the complexity, it's very difficult to derive a relationship between the input and the output. So the advent of the computing high technologies, and of course the knowledge of mathematics and statistics help in bringing out some prediction models everywhere in all fields. Actually, that helps in taking a very useful decision, whether it is in the designing or manufacturing or processing or marketing. Everywhere we have a large volume of data. From the data, we arrive some good models. That models help in predicting what will happen in the future. So that helps us to set right our direction, doing some mid-course correction, so that whatever the venture we involve, so that would become profitable and sustainable. So I again congratulate the Department of Computer Science organizing such a program, and I also request all the participants from all the institute, so make use of the program to the largest extent possible, because the days to come it will be the order of the day. And again I join with our HOD in welcoming again our chief guest Professor Sitabhra Sinha from computational biology and theoretical physics department, Institute of Mathematical Sciences, Chennai. Of course, I am also looking forward to hearing from him. I wish the program a grand success. Thank you.
Thank you, sir.
Thank you, sir. I request Registrar Dr. A. Azad to give the felicitation.
Good morning to all of you. I'm very happy about this program on data. Respected Pro Vice Chancellor of our institute, Dr. A. Pir Mohammed, Dr. Venkatesan Selvam, Dean, Dr. Syed Mohammed, HOD, Senior General Manager, Mr. Jalal, coordinators, deans, HODs, directors, research scholars, teaching faculty, students, and participants from other universities. Once again, good morning to all of you. Coming to our topic, so I'm very happy about the data science as the subject. It is a subject of great relevance today for the business. There are many approaches. One is computational approach, okay, to receive all the data, mathematically analyze and other things. On the other side, you have business requirements. Today, the companies have become very large. From international companies, they have become multinational companies. Some companies' budget are larger than even a few countries put together. Since the corporations have become very large and they are working on different time zones, different parts of different continents, the big data analytics is going to be a great enabler for them to compete in the market. I have already told in another meeting that today, when it comes to large companies, it is your big data versus my big data. So whichever company acquires the data fast, analyzes, and takes action, that company will make a profit. It will be ahead of the competitors. So this also has developed any field, that is, where do you collect data? There are many collect points. Today, if you are using the computer, the data is being collected the moment you start using the computer. So there is a huge competition for data. And then acquisition, how do you acquire the right kind of data? And then finally, interpretation. To repeat myself from my earlier talk, the companies want a single version of the truth. The single version is which product is required where, at what cost, who are the customers. So a lot of analysis has to go if you have to get a single version of the truth. Among the academic community also, there's a huge interest to learn big data because there is a big advantage. Since the big data analytics is only a few years old, there is no one called highly experienced. So if you can enter into this, you will be a leader in big data and big data analytics. But you have to find where is your talent. You cannot do everything. So there are many segments of big data. wherever, whichever is you are comfortable, you have to get into it. Very interestingly, most of the programs, analysis tools, all of them are open source. Today in Chennai or in many cities, you have good broadband facility. So doing big data analytics is not difficult. Information is coming towards you. So definitely it is a field where you can specialize. So I wish the program great deliberations. Wish you all the best. Thank you very much.
Thank you, sir.
Thank you, sir. I, re- I request our Dean, School of Computer Information and Mathematical Sciences, Dr. Venkatesan Selvam, to give the felicitation.
Yes. Am I audible now?
Yes, sir.
Yes, sir.
Good morning to one and all connected here. Inaugural of 1 week online faculty development program on data science, which is scheduled from 21st September to 25th September 2020, sponsored by the AICTE and ATAL, organized by the Department of Computer Science and Engineering, belongs to School of Computer Information Mathematical Sciences. It gives me an immense pleasure to welcome all the dignitaries and participants for this faculty development program on data science. To start with, I welcome the respected chief guest, Dr. Sitabhra Sinha, who is a professor, computational biology, theoretical physics, Institute of Mathematical Sciences, Chennai, who is here to inaugurate the FDP and deliver the keynote address. And to grace this occasion, we have our respected Pro Vice Chancellor of the institution, Dr. A. Pir Mohammed, and respected Registrar of our institution, Dr. A. Azad, and Professor and Head, Dr. E. Syed Mohammed, Computer Science and Engineering Department, and he is the coordinator of the program also, who has given the program objective clearly, what is going to be planned and what is going to be conducted for the entire week. I welcome you, Dr. E. Syed Mohammed, and the program committee members of the department and organizing committee members of the department. I wholeheartedly extend this welcome for this FDP program. As a dean of this School of Computer Information Mathematical Sciences, I had a privilege to share a few words with respect to the topic called as data science. Before sharing a few words with respect to the topic data science, I'd like to thank our management, especially the Pro Vice Chancellor, Registrar, and Senior General Manager of our institution for giving this opportunity, especially for the Computer Science Department and School of Computer Information Mathematical Sciences. And then hearty congratulations and appreciation to the head of the department for organizing this program. And best wishes to the participants who are all connected here in various modes of technology to learn the technology. Coming to the subject of data science, it is one of the paradigm shift with respect to the industry 4.0, which is making the revolution in the current and the future generation, especially in the data analytics and data analysis we call. To call simply the data science, what it will be, it is like interdisciplinary concept by using the scientific methodologies, any mathematical principle, process, methods, algorithms, for the prediction of the current and the future. With respect to the business model, we can say, in the earlier days, there will be a loss while making this business or analytical process other thing. Whereas with respect to this availability of tools and technology, especially this open source softwares like R, Python, and then frameworks like PyTorch, TensorFlow, and other concepts like Tableau visualization tools are there. With availability of this modern tools, the table level itself we can predict what will happen for the current process or the requirement. So that is the beauty of this data science. When it comes to the participant list, I've seen like a more number of faculty members are there. For them, my kind suggestion is that this is a current and upcoming field there is a lot more to enhance your knowledge with respect to this data science. And then more research options and opportunities available with respect to the concept of data science. Only thing is that your involvement and the search and meet the requirement of the industry. So more research opportunities available. When it comes to the current generation of student, there is a good amount of career opportunities. That is, especially the employment opportunities are more because, as rightly suggested by the registrar for institution, this is like 3 or 4 years old concept of big data analysis or business for business intelligence, what we call. So definitely there will be future scope for another 1 decade. So I request each and everyone to utilize this opportunity in dissemination of this knowledge through this FTP faculty development program. I have gone through the content of the program agenda, like itinerary of concepts what they will teach from for the 1 week. So it is well planned by the dedicated and advanced technical faculty members to meet the requirement of the industry. I hope this FTP will fulfill all the requirements of the participants and the need of the institution also within the right time. With this keyword, I like to conclude my speech. Thank you very much for this opportunity. Thank you, one and all. Have a good time. Thank you.
Thank you, sir.
Thank you, sir. I call Dr. A. Ramachandran, Assistant Professor of CSC Department, to give a brief introduction about our chief guest, Professor Sitabhra Sinha.
Thank you, ma'am. I'm audible, ma'am?
Yes, ma'am. Yes, sir.
A very warm good morning. A very warm good morning to everyone. This is my privilege to introduce today's chief guest, Dr. Sitabhra Sinha. He is working as a professor, computational biology and theoretical physics at IMSc, Institute of Mathematical Sciences, Chennai, and also adjacent faculty of NIAS, National Institute of Advanced Studies in Bangalore. He did doctoral research on non-linear dynamics of recurrent neural networks model at the Machine Intelligence Unit in Indian Statistical Institute at Calcutta from 1994 to 1998. He did postdoctoral research on non-linear dynamics of spatial extended systems with focus on biological systems at the Department of Physics in Indian Institute of Science at Bangalore from 1998 to 2000 and 2001 to 2002, and Weill Medical College of Cornell University at New York City from 2000 to 2001. Dr. Sinha joined as a faculty at the Institute of Mathematical Sciences at Chennai in September 2002. An interested area of research like complex systems, nonlinear dynamics, and theoretical and computational biophysics. Currently, his working research areas are physics of cardiac arrhythmias, network dynamics, systems biology, computational neuroscience, physics of social and economic phenomena, emergence of computational complexity in cellular automata and related systems, etc. Dr. Sinha has published 119 papers through reputed international journals and conferences. He published Indian patent entitled on defibrillation and spiral turbulence in the model for ventricular fibrillations, the patent number 199042, date of granted 1st March 2006. He designed the software key core decomposition of protein contact networks. His thought subjects are system biology, mathematical methods, statistical mechanics, and condensed matter physics. Dr. Sitabhra Sinha given a guest speech IIS ER Tirupati at 2017, IMSc student orientation talk at 2016, talk on instability of financial networks, IIS November 2011, ECCS as 2011 network mesodynamic talks, network biology talk second into US Frontier of Science Symposium January 18 to 20, and etc. Dr. Sinha 2013 and 2014 research group members are Sasidevan, Dhanmai, Sridhar, Ashraf, Anand, Sakti, Chandrasekhar, Soumya, Abdul, Janagi, Manu Raju, Venkat, and Jason. Thank you to all for giving this opportunity. Thank you.
Thank you, sir. Now I call our chief guest to deliver the keynote address.
Is my screen visible?
Yes, sir.
Okay.
Yes, sir.
All right. Okay. So first of all, thank you for that very kind introduction. And I would like to thank the Institute for giving me this opportunity of sharing some of our recent work on exploring the frontiers of data science. Given that you have given me this responsibility of delivering the keynote, which would in some sense set the tone for the rest of the meeting, it was a very interesting exercise for me to try to think about the general perspective of some of the research we do. And I welcome this opportunity to share some of these insights with the audience. So when we hear the word data science, there are two aspects of this discipline, right? Data and science. So data is essentially information, right? Any kind of information. It could be information about traffic, it could be information about economic activity, it could be information about bank statement, your purchasing habit, whatever, right? I mean, anything falls under the rubric of data. But the other part of this discipline, science, that's a loaded word, right? And that's precisely where the importance of data science comes from. Because science, apart from its intrinsic value, also happens to be, especially in this age, a driver of economic growth. And so therefore, it's not just for expanding our knowledge, but also for the quality of our life that it is important to allow for rapid scientific progress. In fact, most of history shows that societies which invested in expanding their scientific and technical knowledge also reap the benefits in terms of prosperity. Of course, the best example of this is that the scientific revolution, which happened in Europe during the 16th and 17th centuries, directly led to the Industrial Revolution of the 18th century, and which of course led to the dominance of the West, as we call it, until even today. But today we are faced with another event that can actually become a big opportunity for us. I'm of course referring to the information revolution, which is actually accelerating the rise of the gross domestic product per capita of the entire world. So here I have a figure which shows how, following the scientific revolution and the industrial revolution, the rate of increase of GDP across the world increased, and it's increasing even further at a higher rate as a result of the information revolution. And to further buttress my point about the relation between scientific progress and economic development, let me just show you a very interesting piece of work done by Professor Angus Maddison of the University of Groningen, where he has estimated the gross domestic product of the world right from the year 180, that is, essentially for more than 2000 years, right? So from year one until, in this graph, 2008, he has charted, how the GDP of the entire world varied, and more importantly, how different countries of the world contributed to this world GDP. The most interesting aspect of this entire graph, at least for us Indians, is that until about 1700, India more or less contributed the largest share of the world GDP. China was occasionally, leading India, but for most of this history, for most of this 2000 years, it was essentially just India and China. Okay, sometimes India had the highest contribution to the world GDP, sometimes China, and this continued until almost the middle of the 19th century. So you can see up to 1820, India and China are essentially contributing to, the bulk of the world GDP. And then suddenly, from the middle of the 19th century, you saw an inversion. So suddenly the contribution of India and China to the world GDP started shrinking to the point where in 1970, they essentially, contributed together to less than 20%. It's only since the beginning of this new century, the 21st century, that we have started seeing a reversal of this very strange anomaly that happened in the middle of the 19th century. China, of course, is forging ahead to the point where they're essentially going to become the leading economy of the world very soon. India, although at the moment the economy doesn't seem to be doing too well, of course, has extremely bright prospects. Several historians like Kenneth Pomeranz and others have actually pointed out that the rise of India and China at the end of the 20th century and at the beginning of the 21st century is in fact not a big surprise. The surprise is in fact why the West was so dominant for the last 200 years. That is the real anomaly. The West had never ever been leaders in economic progress. It was essentially the accident that industrial revolution happened in the West, that the West took over the leadership of economic progress from India and China. And it is only right that with information revolution, India and China take their rightful positions in the world economy as the leaders, not the followers of the West. However, like all opportunities, we can't just sit there. We have to grab it by our hands. And it has to be done by developing our infrastructure, not just infrastructure for doing business, but also for our research infrastructure. Now, what does this have to do with science? So as I said, economic progress is very much wedded to scientific progress, and in order to take our rightful position at the top of the world economy, we have to become scientific leaders. If we want to be the leaders of the future technologies such as quantum computing or nanobiotechnology, we have to do something about it. We have to essentially take this opportunity by our both hands so that it can drive us to the pole position of the world economy. However, progress is not inevitable. There have been several instances in the past where societies which have earlier been leaders had lost their lead, had fallen behind. Is there a possibility that the present rate of scientific progress can actually slow down or even stop? So we need to anticipate possible future bottlenecks of the growth of science, and if they exist, come up with solutions. It turns out that the very success of science, the very rapid growth of science, today is threatening its continued progress. And I'm referring to the phenomenon which has sometimes been called the exponential growth of scientific knowledge. This was first pointed out in the 1960s by Derek de Sola Price, a British historian of science who at that time was working at the University of Singapore, who was one of the first people to apply quantitative measurements to how science itself progresses, to, in a sense, applying science to study science. So he's one of the pioneers of the field known as scientometrics. In a remarkable book called Science in Babylon, Sola Price pointed out that in the normal mode of growth of science is exponential. So if you measure scientific progress by any metric, so for example, the rate at which the various elements were discovered, the rate at which new universities are being established, the number of scientific journals that are in existence at any given time, or technical developments like the energy of particle accelerator beams, which are used to smash elementary particles, or for that matter, transistor density on semiconductor chips, and this is of course the famous Moore's law. You find that essentially whatever quantity you try to measure, they tend to grow exponentially with time. So this is shown in this graphic shown on the right of my screen. So if you just look at the number of journals as a function of time, you find that if you plot the vertical axis in log scale and the horizontal axis in normal scale, the curve is essentially a line. What this means is essentially that if you had plotted this in normal scale, if both the vertical and the horizontal axis were in normal scale, you would see essentially a skyrocketing increase in the number of scientific journals. So whatever metric you use, number of papers, number of citations, or whatever, scientific progress in quantitative terms increases exponentially. And you say that's a good thing, right? Why should we be worried? Sola Price pointed out that this is a double-edged sword, right? On the one hand, it's good that scientific progress always increases exponentially, but growth is also a problem. In India, of course, where our population growth is also, extremely rapid, we understand, right, why growth is a problem, because it leads to crunch in resources. Exponential growth cannot continue indefinitely because of limitation of resources. This could be material, this could be intellectual. There's only so many papers that you can read in a year. There's only so many facts that you can retain in your mind. The continued increase in the amount of scientific facts that are accumulating essentially surpasses the capacity of the human mind to comprehend all of them. So Sola Price noted that whenever growth reached a ceiling because of these limitations, progress stops and that area of research dies out. Otherwise, you have to do some technical fix. You have to reorganize or change the technique by which you do research by using new technology, which essentially will then reset everything, and you would have another period of exponential growth and flourishing of science. So the important point is that if you cannot maintain exponential growth, it will die out. So to maintain the continued growth of science exponentially, we require to continually innovate, to come up with new technologies which can cope with the increased amount of scientific knowledge. So is science facing a crisis today? Is it possible that the rate at which scientific progress is happening, we are in danger of reaching a limit to growth and consequently the end of science? Maybe. As I said, it's ironic that the very success of science has made it a victim of its success. So the computer revolution, which essentially really got into swing in the 60s, from the 60s, has allowed us to do things that we have never dreamed of before. So just a few examples: we can simulate the global climate systems. We can essentially do extremely complicated data gathering from particle physics experiments and infer facts that we could never do before the computer came along. We can, sequence the entire human genome. We can start working on the proteome. We can start working on the connectome, the entire database of all the connections in the human brain. All of this the computer has made possible. Unfortunately, while the data that is being generated by the computer revolution is expanding exponentially, our capacity to comprehend that data and to infer patterns, to discover relations between various pieces of information is completely inadequate. There has been no revolution in the way that we look at this information and try to understand it. There has been no revolution in, technical revolution in trying to understand that huge quantity of data that has come. And it seems that without a novel technology to help us obtain understanding from information, and hence the title of my talk, we are in real danger of putting an end to science as we know it. And in fact, about a decade back, Wired magazine ran a feature article called The End of Science, in which Chris Anderson, the author, argued that whereas earlier scientific progress was limited by the amount of data that was available, okay? So, like if you want to do the astronomy, you take your telescope, you look at the sky, and there's only so much you can observe, right? And then you can, think in leisure about, what is it that you saw. Or if you're doing, if you're a life scientist, you go to your lab and you peer through a microscope, and whatever you see, you make drawings of, and you start thinking. Okay, and that was it, right? So obtaining data to verify the theories that various people posited, that was the bottleneck for progress. So theories came easily. People would come up with all kinds of theories, and then they have to wait around for people to actually verify them using observations and experiments. Now the situation has reversed. Data is cheap, so more and more data is becoming available, and we have to really accelerate our game to come up with theories to explain the data. So this is a complete inversion of the way that science was being done until about the 20th century, which is why science as we understand it, based upon the model of science that we have seen being practiced in the 20th century, may be becoming obsolete. Okay? So this is a really, really old image by now. So this is almost a decade back, but even a decade back, it was pretty clear that how much data was actually being generated as a result of the computer revolution. So at that point, you had this 1 terabyte, which was a hard drive which could hold essentially lakhs of songs. The amount of photos that were uploaded at Facebook each month at that time was 20 terabyte. I mean, now no longer we even need to talk about what a huge amount of photos that are uploaded in the various social media sites like Instagram, for example. Okay, and so it's no longer even decade back, we could no longer suffice with just megabyte. We had to come up with terms like terabyte and petabyte and so on. And now we are talking about exabytes. Right? So how do we handle this data deluge? And as of course, all of you understand, because the meeting is about data science, that it has been suggested that the possible answer is this supposedly new field called data science. So what is data science? In a sense, it's actually trying to solve a very old question. And that question is as old as science itself. You have a set of simultaneous observations of multiple factors, call them X and Y, or it could be X, Y, Z, or it could be, whatever, n number of different factors. Question is, you have these observations, how do we relate them? You might ask, why do we need to relate them? We need to relate them because otherwise we'll have to keep in mind each of these observations, which is a huge drain on our memory. Okay, so suppose, imagine that you are a primitive human and you are faced with a life and death situation. Okay? And what's that life and death situation? Anything. It could be a wild animal which is in front of you, okay, or it could be another human with a club raised in his hand, okay, and you have to, in a split second, decide what's the right response to that life and death situation. Do you run? Do you pick up a stick? Do you pick up a stone and do you throw it? What's the right decision, right? Now, presumably, that is not the first time that this has happened to any human, right? So earlier also, either you or another human has encountered a similar situation. So this means that you have a database of previous observations of similar situations, and you have some understanding of what responses worked and what didn't. Okay? So call X this observation, this circumstance, okay? The circumstance in which you face yourself, find yourself, and Y the responses that worked. Okay? Now, in order to figure out what is it that you should do at this present circumstance, you can either try to think of all the previous incidents that you remember of, a similar incident that happened, and try to figure out, okay, which incident was the closest to what you have today, and then remembering what response actually worked in that circumstance. This will of course take a huge amount of time because fetching all this information from your memory and then figuring out, okay, what is the one which is the best in terms of the current circumstance. All of this takes time, right? By this time you'll be attacked and probably dead. A better or more efficient method is if you can actually figure out a function which best fits all of these observations, X and Y. So for example, here it could be a straight line, right? And so given the straight line, essentially that means that you now have a law, and I say law within quotes, okay, which relates the circumstance with the right response. So now you don't have to remember all these individual instances. All you need to know is this law. And what you need to do is you need to plug in the variables of the current circumstance into this law and just read out the correct response from the function, right? So it may not be a life and death situation. You could be like, peering out at the sky and trying to decide, do I take my umbrella? Okay, so if I take my umbrella and it doesn't rain, obviously it's a hassle, right? Carrying that umbrella all day and I might lose it. But if it is going to rain and I don't take the umbrella, I'm going to get wet, right? So what do? I look out my window and look at the sky and see, how much cloud coverage is there, whether there's kind of a storm brewing and so on. And based on that, I decide whether to take my umbrella or not. So basically what's going on in my mind is, of course, I am using a mapping between the cloud cover, whether the sun is covered or not, whether there's a wind. So all this multivariable, data. I'm dealing with all this unconsciously, of course, but what I'm doing is I'm taking this multiple factors in, and I am outputting a single response, which is a yes or no answer. Do I take my umbrella? Don't. Okay. So in a sense, we do this unconsciously all the time. Our brains are excellent at doing these kinds of generalization or abstraction from observations in order to come up with a general law. Okay, so we don't consciously remember all these previous instances in which we had seen a similar sky and whether it rained or not, and consequently whether we take an umbrella. We do it in a split second, right? And that's because our brain has essentially computed this function implicitly, which relates all these multiple variables, amount of cloud cover, whether the sun is visible, whether the breeze is blowing, with the probability that it's going to rain, and hence whether I should take an umbrella or not. Now, when you formalize this procedure, when you no longer do this unconsciously, that's when you have science. Okay? And I would like to point out that, therefore, in a sense, data science is not a new discipline. It's in fact as old as science. So if you remember the story of Galileo and how he came up with the idea of the pendulum clock, what did he do? Well, when he was a teenager, he was in this cathedral in Pisa where he saw a lamp hung from high above the ceiling, which is swinging in the breeze. Now, all of you have seen similar events, right? But Galileo actually was curious that is the time that the pendulum takes to swing from one end to the other different as the amplitude of the swing becomes smaller. So he timed the period it takes for this chandelier to swing from one end to the other using his pulse. And he noticed to his surprise that no matter how much it swung, whether it swung wildly from side to side or whether they were very small swings, it took exactly the same time. He went back home and started cutting out threads of different lengths and putting weights at one end of these strings and started experimenting by getting them to swing and see how long it took. And what he found was that the time period of the oscillation, that is the period of time it took for the weight to go from one end of the swing to the other end of the swing, was related to the length of the pendulum in a very curious manner. And the rest, as they say, is history. So he figured out that the time period is in fact related to the square root of the length of the string. And this eventually led, for example, to the pendulum clock when Christian Huygens in Netherlands heard about Galileo's result and Galileo's observation that maybe one can actually use the pendulum to regulate the timekeeping of mechanical clocks. So Christian Huygens took Galileo's theoretical suggestion, put it together, and you had the first pendulum clock, one of the first accurate measures of time. So it's easy to do this kind of relating multiple factors if you have a small number of factors. So for example, here if you look at X and Y, no prizes for guessing that, the first thing you'll try to do is fit a straight line. And you say that, okay, X is related to Y linearly. And the human eye is a fantastic pattern recognizer. It is better than any algorithm for pattern recognition so far invented. However, the problem is the moment the number of relevant factors become large, even larger than 3, we are no longer able to discern identifiable patterns. That is because our visual capability has evolved to spot 2-dimensional or 3-dimensional patterns. We are very bad at visualizing high-dimensional spaces because in an evolutionary sense, we never needed to think about high-dimensional spaces, right? Most of our life is carried out in a 3-dimensional space. However, the moment we start thinking abstractly, about factors and so on, we have to deal with a very large high-dimensional space where each of the axes corresponds to a particular factor. So we need to reduce the number of relevant factors and bring it down to 2 or 3 to be able to discern a pattern in the data. So if you are confronted with a problem, you know that there are many confounding variables, right? So for example, Galileo, for example, I'm sure thought that maybe the weight of the chandelier might have a role to play. And it took him some experiments before he realized that the weight of the bulb actually has no role to play. Okay. So most of the scientific inside business is about figuring out what factors of the problem are irrelevant. Okay. So as they say, you essentially discard everything that is unnecessary, and then you are left with the gist of the problem. And then you try to solve that problem, and often it turns out that this reduced bare-bone problem is much easier to solve than what you had seen earlier with all those factors put in. Now, this is where scientific genius comes. The reason why we remember Galileo is because he could look at this phenomenon and figure out through observation and judicious experiments that everything is irrelevant except the length of the pendulum, except the length of the string. Right? And that's in a sense what data science is about. Right? You have at one end access to high quality, large volume empirical data from which you are trying to infer patterns. Okay? So essentially you're trying to generalize from large number of observations. So you infer general features or what we might call them stylized facts, and using this you build a model. The model may be formal or it may be an informal model. So what I mean by informal model, well, when you look at the sky and you decide whether to take an umbrella or not, what you're using is an informal model. If I ask you to write down in terms of, let's say, equations, what is the problem that your brain is solving in order to come up with the probability that it will rain, you won't be able to say it. But nevertheless, you actually take the right decision most of the time. So that means you have an effective model. Okay. So we are engaged in model making whether we are conscious of it or not. And so what do? We use that model to make predictions about what is the right response. Sometimes it works, sometimes it doesn't. Whatever happens, that becomes another observation. And so when we refine based upon our, whether our response worked or not, we refine our model. Right? And that's how progress happens. And a classic example of this is how classical mechanics developed. So before Newton, before Kepler, there was this gentleman called Tycho Brahe. He was an astronomer, but he didn't have telescopes. What he did was he just observed the night sky using graduated instruments like the one that you see in the figure on the left. Okay? But instead of just looking at the night sky and saying, oh, there's Venus, so there's Mars, he actually made extremely accurate measurements of precisely where in the night sky each star was located. And he noted this down. And that essentially corresponds to the first step in this procedure of data science. He collected high quality, large volumes of empirical data. Now, Tycho had an assistant, and this assistant's name was Johannes Kepler. After Tycho died, Kepler used the data that was collected by Tycho Brahe to come up with some generalizations of his observations. So he said that, look, yes, on this day, this star was in this position, on this day, the star was in this position, and so on. But instead of referring to this data all the time, can I actually come up with a general law which says, okay, this is exactly how the star seems to move. And he came up with 3 generalizations which are known as Kepler's laws. The first law said all planets move as ellipses with the sun at one of the foci. The second was that if you connect a planet to the sun with a line, then it will always sweep out equal areas in equal times. And third, if you square the period of any planet, you will find that it's proportional to the cube of the semi-major axis of the elliptical orbit. Now, these are remarkable observations, right? Because, if you just look at Tycho Brahe's tables, these were just rows and columns of numbers, numbers upon numbers. Kepler looked at those numbers for years, and then suddenly this pattern jumped up to him. Okay? And that's where scientific genius comes in, right? So you had the second step of the data science process. Kepler inferred general features or stylized facts. And then you have to come to this gentleman, Isaac Newton, who in the 17th century gave a formal theoretical framework which explained not only Kepler's laws, but by extension, all the data that Tycho Brahe had collected. So you no longer needed to remember all this data anymore. So you only need to remember the Newton's laws of motion, and you will be able to infer all those data and observations that Tycho had collected so painstakingly. Okay? So you only need to know, for one, a body at rest remains at rest, and a body in motion remains in motion with a constant speed and in a straight line, unless it's acted upon by an outside force. That's the first law. Second, that the force that is acting on a body is a product of the mass of the body and the acceleration of the body. That's the second law. And the third law says to every action there is an equal and opposite reaction. Add to it the law of gravitation that Newton had independently discovered, that the force of gravitational attraction is actually proportional to the product of the masses and inversely proportional to the square of the distance between the masses. And you had a coherent theoretical framework that can explain the motion of the celestial objects. And so this completed the model making part. And of course, using these models, people started predicting where a particular planet is going to be at a particular point of time. And the moment there would be deviations from the predictions, the moment someone observes something which does not match with the observation, they'll say, anomaly. Maybe there's something there which we missed. And so this is how, for example, people discovered the planet Neptune, right? Neptune was never observed before it was actually posited. Its existence was said to be an outcome of the fact that without a planet being there, you couldn't explain the divergence of the observation of the position of Uranus from what was being predicted by Newton's theory. So you could predict that a planet must be there just based on the fact that observation was not matching what theory was telling you. And of course, in the 20th century, when people discovered other anomalies, Einstein came up with the theory of relativity. Right? So you have this process of prediction and refinement going on in the science that we are not very familiar with. So data science is actually not very different from science as it is practiced until the 20th century. So what's different? And what's different is that you needed geniuses like Kepler and Newton to do this. Can ordinary mortals do this with some help from something known as a computer? In other words, can you replace genius with computers and automated algorithms? Can we get insights from very high dimensional data, huge quantities of data, by taking the help of computers and algorithms? And that's essentially what data science is all about. So I've spoken mostly about very abstract concepts until now. So in the remaining time that I have with me, I will actually talk concretely about one particular aspect in which we're using data science to infer laws in the spirit of Newton. However, this is something that we could not have done without the computer revolution. It's the access to cheap, easy computing and the availability of large quantities of electronic data that actually has made it possible for us to actually sift through this data in order to come up with laws which govern this particular phenomenon. So this field, sometimes called economophysics, so this is a book, introductory book that we wrote some time back. If you're interested, you can take a look. Essentially asks, are there laws that govern financial markets? So this is the New York Stock Exchange, a couple of decades back. Now, of course, it looks quite different. So can we infer the laws of finance from the data that is generated by the market every day and every second? So the statistical analysis of financial data is, of course, not completely new. Financial data has been available on a daily basis since 19th century. So if you are familiar with names like Illustrated London News and so on, and you go to the historical archives of the 19th century, you would find that even long back, they used to give tables of financial data. However, what happened was that in the 80s, suddenly you could get access to data with, sub-minute sampling rate. Okay, you suddenly have data which was available at, frequency of less than a minute. And since 93, we actually have data for each transaction, what we call tick by tick. Okay? And this access to extremely highly resolved data, and of course the ability of computers to analyze that data, actually has made it possible to come up with general features of how markets work. Now, of course, you might say, why actually do you need to analyze all this data? Let traders trade. Well, there are fundamental reasons. We want to understand markets because, after all, financial markets drive today the entire economy of the world. So we would like to know really whether markets are inherently unstable, whether the kind of crash we saw in 2008, 2009 is something that can happen time and time again. And can we come up with some measures which will tell us when the next big crash is going to happen so that we can take steps to avoid it? But of course, it's not just all these big questions that motivate people to look at patterns in financial data. There are also applied reasons. So you could be a broker, or you could be the member of a financial analytics company who would like to know these patterns because it will help you to price options. So for example, in option pricing formula, a big unknown is volatility. How much volatile is financial movements? And how do you estimate volatility? So that turns out to be an extremely tough problem. So if you have if you can figure out a good method of estimating volatility by looking at all this data and their patterns, you can actually come up with a killer option pricing formula, something much, much better than the Black-Scholes formula that most people use. Or you could be a portfolio manager. You could be managing a mutual fund, right? And what is the issue here? Well, you would like to pick stocks for your portfolio which will maximize your returns while minimizing the risk. So you might be tempted to buy lots of Reliance shares, but if you only have Reliance shares in your portfolio, that's a very bad business decision because something happens to the Ambanis and your entire portfolio's value goes to zero. You don't want that, right? So you'd like to pick stocks such that even if some of the stocks do very badly, other stocks will do well, and so on average, you'd remain above water. So what does financial data look like? Well, there are different types of data. So one is, of course, the order book, in which you have records of every transaction. For example, the buy limit order or the sell limit order, which is coming at each instant. So limit orders are essentially, like some instruction from a principal to the agent say that, if the price of the stock falls below this price, buy this many quantities, or if the price of the stock goes above this price, then sell this quantities. Right? And so there's a gap, of course, between the highest buy limit order and the lowest price sell limit order, and this is called the spread. So, typically there will be a market order. So someone will come into the market and say, no, just, I want to I want to buy so many shares at the best price available. So what will happen is, this guy just goes and buys up the stocks which are available at the lowest price. So suddenly some of your sell limit orders disappear and your spread changes, right? And so you can record these changes in the spread, and the midpoint of the spread is essentially the price of that particular stock at that particular point of time. So you can record the value of an asset. It could be a stock, it could be an option, or it could be a bond, or whatever. Okay. And you could record these activities, and you could record the price. And so this is where we come into the trade book. So the trade book essentially records every single transaction that has happened. So you would have the date, you would have the time, you have the price at which the stocks were traded, and how many stocks were traded. And you can plot something which looks like this. You have a price variation over time. So this is, of course, an hourly average over how the price was fluctuating, and you can see it fluctuates enormously, right? Even after taking an average over each hour, it's still appearing to fluctuate a lot. And if you look at the activity, you find that that also tends to fluctuate enormously. So sometimes you have a huge amount of stocks which are being bought and sold, and sometimes very few stocks are being bought and sold. So you might be interested, for example, to figure out what is the distribution of these price fluctuations. How much do the prices vary? Do they vary over a small range? Do they vary over a large range? Okay. Now, ever since a French mathematician called Bechellier wrote his PhD thesis in 1900 on the random character of the stock price evolution. So basically he said that, look, since a large number of people are buying and selling a stock at any given time, and presumably they are not, all thinking the same way. Everyone is acting independently, and so you can assume that, on average, the actions taken by some would be cancelled out by the actions taken by others. So essentially, I can view the price of a stock, which goes up if more people buy, and which goes down if more people sell. And since this is happening purely at random, I can say that this price is going to move up and down in a random fashion. So I can study it as a random walk. Okay. So ever since Bacheliers' time, people have tried to understand this as a random walk, or we have a technical name for it, that the fluctuations are Gaussian noise. But there's a problem. Gaussian noise essentially means that there should be no large events. But if you look at some real data, if you look at, for example, how the Reliance share, how it fluctuated in price between, let's say, November 1994 and January 2006, you find that it actually most of the time has small fluctuations, but occasionally it has extremely large fluctuations, and this is occurring much more frequently than would be predicted by the random walk model, which has been the model believed by people working in the markets ever since 1900. And so this is where data science first came in, to try to understand how do prices move. Do they move, as Bachelier said, as a random walk, or do they have some other behavior? So it turned out, and this was work which was pioneered by the Italian physicist Rosario Mantegna, who at that time was working with the American physicist Gene Stanley at Boston University, that the distribution of price fluctuations, in fact, do not follow a random walk. They follow what is known as a power law, or as they call it, the inverse cubic law. Now, why is this of interest? Why would you say, why would a trader be interested, whether it's a random walk or a power law? Well, it turns out that if it's a power law, it's very likely that we're going to have enormous fluctuations within a reasonable period of time. So if you are, for example, a trader, and let's say you know that a stock that you're interested in has prices which are fluctuating as a random walk, what does that mean? It means, in effect, that if you know the mean and the standard deviation, the variance of these price fluctuations, you know that the price is very unlikely to go above twice the standard deviation or below the twice the standard deviation. So this is the plus minus 3 sigma limit that we talk about. So 99% of all observations in a Gaussian process, in a random walk, would fall within the plus minus 3 sigma limit. And so you'd say that, well, the possibility that you're going to have a greater than plus 3 sigma deviation in the price is minuscule. However, if it's a power law, it turns out that it's no longer only less than 1% probability that the price is going to be higher than plus minus 3 sigma. It can be as high as 10% probability, okay, depending upon the nature of the power law. So this was a revelation when it first came, when first Stanley's and Mantegna's group reported in 1999 that actually distribution of prices do not follow a random walk at, if you look at it very carefully over very short time intervals, but actually it follows a power law. And this is how we actually came in, because Stanley's group actually did an analysis later of Indian markets, and they came to the conclusion, well, the Indian markets are actually different. Maybe they follow a random walk, and they tried to connect it with maybe it's because Indian markets are emerging markets and so on. So in 2007, with my student at that time, Rajkumar Pan, we showed that in fact Indian markets also follow a power law, and not just any power law. It actually follows this inverse cubic law, which characterizes the New York Stock Exchange. Okay? And so this actually made us compare the American market price fluctuation behavior with the Indian market price fluctuation behavior, and we showed that they are essentially identical. So here I have two sets of data points in each curve. So this is the positive part of the positive fluctuations where the prices are going up, and this is the negative fluctuations where the prices are going down. And there are two types of points, data points here. So one is circle, one is diamond. So one is standing for New York Stock Exchange, one for National Stock Exchange. You can see the points just fall on each other. So in terms of price fluctuation, emerging markets behave exactly identical to developed markets. So it seems that price fluctuation at least is universal. So have we come up with some kind of a universal law then? Well, there's a teeny weeny problem, because if you ask an economist, they'll say, well, it works on the financial market. They'll say, well, look, the price of an asset is actually decided by its underlying value, and so return should be related to the changes in the fundamental value of the stock of the company, and these are exogenous. So what happens to a company's stock presumably is dependent upon things which are not only happening inside the financial market. It could be also something happens to the principle of the company. So in the example I gave, something happens to the Ambani's, Reliance shares take a dip, right? And these are entirely exogenous influences. This has got nothing to do with what is happening inside the market where traders are trading with each other. So how does that make its appearance in the price fluctuation? So a couple of years back, with a postdoc, Abhijit Chakrabarti, and my project assistant Soumya Yasharan, we started looking at the foreign exchange market. The foreign exchange market is actually the biggest financial market in the world, because it's not confined to any single geographic location. It's not like New York Stock Exchange only in New York trading mostly American stocks and so on. It's actually a decentralized market which is there across the entire world, where buyers and sellers are exchanging different currencies with each other. So there's a huge quantity of data, and what we found was that indeed there are subtle deviations from the inverse cubic power law. Okay? So some currencies show extremely fat-tailed behavior, so very large deviations from Gaussian behavior. Other currencies, the developed currencies, show much closer agreement with random walks. Okay? So what's going on here? So we found that indeed there are deviations, but actually you can explain the deviations from the power law by looking at the underlying factors. And so what are these factors? Well, one measures how prosperous the country is whose currency we're looking at. So it's gross domestic product per capita. And the other factor is how diverse is the economy of that country. So if you look at what that country is exporting, so it could be like Saudi Arabia is only exporting oil, right? Or Venezuela is only exporting oil. But if you are, let's say, United States, you're exporting all kinds of things. You're exporting electronics goods, you're exporting cars, you're exporting apples. Okay, so not just high technology products, you're also exporting vegetable farm produce. You're exporting milk. So you've got a huge diversity, right? And it's kind of natural to think that if you have a very diverse economy, then if something happens to depress the import or export of one particular product, it's not going to affect your economy much. You're still going to survive, because you can switch your efforts to that other kind of product. So taking this account, the prosperity of the country and the diversity of its economy, we found that both of this actually affect how much the fluctuations of its currency is going to deviate from this inverse cubic law, this universal law. Okay? Actually, what we found was that currency markets don't follow the inverse cubic law. It's actually following something else. It's following something we call the inverse square law. Okay? Sounds very Newtonian, right? So Newton is famous for his inverse square law. So we had this delusions of grandeur when we came up with this word, inverse square law. And so what we find is that you can actually infer exactly how much you're going to deviate from the inverse square law if you know the prosperity of the country in terms of the GDP per capita and the diversity of exports by the Thiel index, which measures the diversity of the export across the country. It turns out that this is not just true for stocks and bonds and commodities and foreign currency, foreign exchange. It's also true for electronic currencies like the Bitcoin. So when we looked at the Bitcoin, and this is work done with summer student Manu Dikshit and project assistant Sonia, we found that this also actually follows a power law tail, and it in fact turns out to be an inverse square law. So it turns out that even though Bitcoin seems very different, it's a new thing in town, everybody's saying, okay, it's the future of currency. When it comes to price fluctuations, it's behaving essentially similarly to all this, older financial assets that we talked about. So it looks like that there is something fundamental about the laws that we have discovered. This inverse square law, the inverse cubic law, is not just true for a particular class of assets, it's absolutely true for all kinds of commodities, financial assets that people can actually trade with each other. You can, if you want, extend these insights further. So for example, you can start trying to understand how does a market behave. So for example, market of course has lots of traders buying and selling with each other, but that's too complicated description, right? You don't know what each trader is doing. But you can know how these traders are affecting the prices of the stocks because they're buying and selling stocks. So instead of looking at the traders, you can look at how the stocks are moving up and down, and you can formulate some kind of effective network of interactions between stocks. So now the question is, how do we identify the network of relations between different stocks in terms of how similar the price movements are over time? And the answer is, well, we can use one of the most fundamental tools for data science, which is the looking at the correlation of these price movements and then looking at their eigenvalues and eigenvectors. So basically you apply linear algebra. And this is why linear algebra is one of the most fundamental things actually in a data science course. Okay, so without any details, because I'm out of time, let me just tell you, we did a correlation analysis, and you cannot just use raw correlations because we know that even uncorrelated signals can actually spuriously show some correlations if you have two short data sets. And so you have to do all this fancy linear algebra. Anyway, we do a lot of fancy linear algebra, and then we come up with a market structure for the Indian market. And remember, this was done in 2007. We have also done it more recently, and we found that unlike the New York Stock Exchange, where you find clusters of stocks which are moving together clearly corresponds to the financial sectors to which they belong. So for example, all insurance stocks move up and down together, all energy stocks move up and down together, all technology stocks move up and down together, all healthcare stocks move up and down together. For the Indian market, actually, there's not that many stocks which are clearly moving together. They're more or less independent. However, exceptions are information technology stocks, which are tightly correlated in their movement, pharmaceutical stocks, which are also tightly correlated in the movement, and petrochemical stocks. So these, not surprisingly, are also the ones which saw the biggest amount of investment in the 1990s and early 2000s. Okay? So this gave us an idea that can the fact that stocks are showing increased clustering indicate that markets are gradually evolving to become more and more developed? Given that New York Stock Exchange has more clusters and Indian market has fewer clusters, could it be that as Indian market develops, we'll see more and more clustering? And this is what we saw 10 years later when Sonia and another summer student, Arya Datta, looked at the National Stock Exchange data from 1996 to 2016. So we found that just as before, information technology and pharmaceutical company stocks continue to retain this distinct character. However, other clusters have also emerged, like the finance sector, like the industrial sector, and so on. And this led us to a study of how exactly a market evolves over a long span of time. So for this, we essentially looked at the New York Stock Exchange, for which we obtained data from just before the Great Depression of 1929. So we had data from 1925 all the way up to 2012. So this is work done with my PhD student Chandrasekhar Kumati and an economist at IIM Ahmedabad, Anindya Chakrabarti. And what we found was that there were some very peculiar behaviors happening in the correlation precisely when large crashes in the markets happened during the Great Depression and during the 2007-2009 crisis. So we characterize this by a measure which is known as structural balance. So since I'm out of time, I will not go into the details of the structural balance. Just suffice to say that essentially we looked at something called balanced triad and unbalanced triad, and we found that during the great crash of 1929 and during the 2007-8 crisis, only during these two periods, we had a huge number of unbalanced triads, which showed that actually you just crawling through the data, you can come up with quantitative indicators of when systemic risk is building up in the market, so you can actually try to predict when the market is about to go south. Okay, so I'm sorry for going out of time, but let me just summarize by saying that just as the large volume of high quality data which is collected by Tycho Brahe transformed astronomy into science by allowing the formulation of laws by Newton, which related all these observables, the availability of high frequency data from markets and the availability of cheap computation power to analyze these patterns hidden in them has given us hints about similar existence of laws in the behavior of traders, in laws of markets, so to say. So we find that the distribution of price fluctuations is described by a power law rather than a random walk. And while markets like NYSE, New York Stock Exchange, and the Indian market do not differ all that much in terms of their fluctuations, if you look at the network, which relates how these stocks, move up and down in terms of their prices, that actually can signal how developed the market is. Moreover, by looking through these patterns, we can actually identify signature of stress, exactly when systemic risk is building up, so that we can identify when the big crash is about to happen. So let me conclude by quoting something from one of my favorite scientists, Dr. Jacob Bronowski, mathematician, philosopher, and historian of science, and is also responsible for possibly the best TV series on science ever made, Ascent of Man. So he concluded this TV series with the following words: "We are a scientific civilization, a civilization in which knowledge is crucial. Science is only a Latin word for knowledge. Knowledge is our destiny." But he also pointed out in that same episode that advancement of knowledge with time is not always inevitable. Scientific progress can falter and humanity can end up in centuries-long dark ages, as has happened multiple times before in our history. So to grasp our destiny of ever-increasing knowledge, we need help. And this help could be obtained from the same technological developments, namely computers and data handling algorithms, that has made the old methods by which we acquire, share, and create knowledge inadequate. So let me thank you for your attention, and I'd like to conclude by thanking all my collaborators who actually helped me to glean all these insights that I briefly mentioned. So Raj, my PhD student, who was very much involved in this work on price fluctuations and also the initial part of correlations, and the more recent work on correlations was done by Sonia and Chandrasekhar, and Anindya has actually carried this forward to analyze the long time historical evolution of New York Stock Exchange. And of course, I'd like to thank generous funding from the Department of Atomic Energy, Government of India, through the Center for Excellence in Complex Systems and Data Science, established in the Institute of Mathematical Sciences, which has made all this possible. So I'd like to apologize again for going over time, and I'd be happy to answer questions if any.
Dear participants, you can unmute yourself and you can ask any questions if you have. You can post in the chat box also.
Thank you, sir, for your nice presentation.
Thank you.
Sir,
Yeah.
I now call Mrs. R. Akila, Assistant Professor, Senior Grade, CSE Department, to give the vote of thanks.
Sorry, was there a question?
No, sir. No, sir.
Okay.
No, sir.
Okay. Thank you. Thank you.
Thank you, sir. Thank you for coming. And you have done a
Thank you.
very nice presentation for us. And we have learned many more points from your presentation. Thank you, sir.
Okay. Thank you so much. So I will stop sharing my screen.
Akila, ma'am.
Thank you, sir. Thank you, participants, for joining this inaugural session and listening to this guest speaker keynote address. And we thank everyone for making this inauguration session a great one. Thank you.